Thank you very much, Giovanni. Thank you very much, Maurizio. You know, so yeah, the topic of today's lecture was was given to me Axions as Axions in Cosmology, but since this is an astrophysics week, I thought maybe I should try to do something related to Axions in Cosmology and astrophysics, and I thought that it might be the most interesting chunk of what I can say about cosmology would be about axion mini clusters. Because they can have astrophysical implications, and I'm not sure other people are going to cover them next week. However, I've also been working a lot in general in the post-inflationary scenario, and we are about to put up a paper also on the axion emission by cosmic strings. So the talk is going to be a melange of cosmic strings and mini clusters. And since I have here my favorite collaborator when it comes to mini clusters, I asked him to drive the discussion on mini clusters himself. So we split the task in such a way. So this is my to set the stage of the discussion. I would just say that why do we study axion cosmology? And I would say because I think it's an excellent opportunity to find whether the QCD axion exists or not. I'm a particle physicist by training, and I really want to know whether the axion is responsible and the particular mechanism is responsible for the solution of the strong CP problem. And I also want to discover a new particle, or as many new particles as possible. So I want to find the axion, and in cosmology we have a fair chance of doing that. Moreover, it turns out that the axion could be the dark matter of the universe, and I would also love to solve this puzzle in a particle physics oriented solution. And this scenario, the axion dark matter is a very plausible scenario. And third but not least, I wouldn't mind to learn a little bit more about cosmology, but I'm a particle physicist. So if I don't learn cosmology and I discover new particles, I would be fine. I would be fine about it. But axion cosmology is a way in which I can have the three things in one. I can perhaps discover the dark matter. I can discover the solution of the strong CP problem, and by learning a little bit about this, I could also pinpoint how the early universe or the aspects of early universe are. So I think it's a fantastic output, and I think it's very motivating to do this axion cosmology due to these three potential benefits. Now, unfortunately, axion cosmology has huge amount of possibilities, right? So, and actually, there's not much conclusions that we can extract once we put all the possibilities on the table. So the possibilities are such that if we observe something, we cannot, well, typically we cannot conclude anything, right? From the observation or non-observation of anything. And moreover, it's extremely complicated to span to search axions in all the parameter space where could be found, or they could have implications in cosmology. So here's where I feel particularly inclined to study the post-inflationary scenario, in which we are going to spend most of the all this discussion. And this is because the post-inflationary scenario gives very clear predictions. It gives us, in particular, two very important predictions. First of all, it would tell us what is the axion dark matter mass. So the mass that the QCD axion needs to have in order to give us all the dark matter in the universe, all the dark matter that we observed. And this is extremely important because if we pinpoint this from cosmology, then we can ask our experimentalists, please do this experiment at this mass, and this could accelerate the experimental discovery of the axion if this particular scenario is realized. Unfortunately, as you know very well, the contribution of axions, of dark matter axions from cosmic strings is uncertain, and there's a lot of simulations to be done. And then, of course, even in this scenario, there's some cosmology dependence. So So we have like a standard model of cosmology in which we have radiation domination happening before BBN and to a very early period of reheating, in which we can give a very nice prediction for the action dark matter mass in principle. But if there's some additional physics, we will have some cosmological dependence that I will not be discussing about in this talk, but we can, of course, talk about. And the second implication is the existence of mini clusters. So this is generic from a post-inflationary scenario, and in particular in radiation domination, we can also make predictions about the existence of small dark matter halos that I would say that they are also the smoking gun of this particular scenario. So if we find the axion dark matter and we find signals of mini clusters, we know that axion, so we will know that this scenario was realized, we will know something about cosmology. But also, even if we don't detect the QCD axion, we might detect mini clusters, and they are a generic prediction of this scenario, so they would be a smoking gun of the existence of axions and this scenario at the same time. So they are possibly very important, but they're also equally hard to simulate, characterize, and they're hard to detect. So let's talk about all this. So let me just start with the axion dark matter mass predictions from cosmology. So here I have a list of the values of the axion dark matter mass that the axion would need to have in order to have the full amount of dark matter observed in the universe, according to different cosmological scenarios. For instance, in the pre-inflationary scenario, since if we could make a prediction of the initial misalignment angle, we could pinpoint the axion dark matter mass with a few percent of uncertainty. But since we cannot generally know the initial condition of the axion field, we have typically 2-3 orders of magnitude uncertainty if we don't assume that the initial conditions for the axion field were tuned either to 0 or to pi. If we allow more tuning, we can span all the parameter space that is allowed for axion dark matter, unfortunately. And here you have also what happens if you allow non-radiation domination cosmologies to deplete the axion or change a little bit the moment when the axions become dark matter. So essentially, the axion dark matter mass shifts to higher masses if you have the axion starting to oscillate or behaving as dark matter during a period of kination. And you have a depletion of axion dark matter if there's some entropy injection, like for instance in a period of matter decay, and then you need to go to smaller masses to compensate the decrease of axion dark matter from matter decay. So this is for pre-inflationary, and if we are in the pre-inflationary scenario, there's little hope of predicting the axion dark matter mass. But in the post-inflationary scenario, we have so much small discrepancy. We have predictions that range between 10 to the minus 5 and 10 to the minus 3 electron volt. This is 2 orders of magnitude, and here we have a hope of actually decreasing the uncertainty and pinpointing the axion mass at least to the percentage, to the few percent accuracy where we know which is typical of the case when we know the initial conditions. Okay. The problem here is that when we do this average over initial conditions, in the post-inflationary scenario, we have a network of topological defects that is created with the axion field, and depending on the theory or the simulations that you analyze and what choices you make, you might end up with different values of the axion dark matter mass. But this is our best hope to pinpoint the axion dark matter mass. If the number of domain walls is larger than 1, again, even if this post-inflationary scenario is very uncertain, because the axion dark matter abundance might end up depending on how you break the degeneracy between vacua of the QCD. Yeah. These ones? These are lower. These are lower limits. Yeah. So this is another version of the same plot, publication, so ranges of axion dark matter mass as a function of publication year, and the latest papers coming from some of our colleagues in the audience, Hari Bilador are here, and Bushman et al., the American group doing numerical simulations, they have non-overlapping estimates for the axion dark matter mass, and this is related to the fact of related to the way in which they extrapolate the results of their numerical simulations. So let's try to understand how this works. First, a picture of the post-inflationary scenario. For those of you who are not acquainted, this is for you to be a bit more relaxed. I introduce you to the scenario. So in this scenario, we have the axion starts to be a field with particle type properties after a Pacheco phase transition that happens after inflation. And after this phase transition, the axion field takes so initial conditions which are uncorrelated are the horizon size, and at the same time, a network of topological defects, particularly global cosmic strings, is formed. Now, this network of cosmic strings might form at a redshift that is as large as 10 to the 25. And for most of the history of the universe, at least for something like 13 eFols, or half of the history of the universe, the network of topological defects might be a subdominant component of the energy of the universe, because the universe is dominated by radiation. And one can show that the energy density in this, the network of topological defects evolves in a particular way. And there's which is called scaling, in which typically when one ends up having something like one string in the Hubble horizon, in the causal horizon. And there's no way to avoid this string until the QCD potential, or the QCD effects make the axion potential relevant, and then the QCD favors the state that minimizes the energy, which is also the one that minimizes the violation of CP, which is theta equals 0. And then at this time, domain walls form. These domain walls pull the strings, and the strings get destroyed. So we are left mostly with oscillations of the axion field around theta equals 0. We have a small period where nonlinearities in the axion potential are relevant, and we will talk about them. They have some implications, but after this small period of nonlinear evolution, we are left with an axion field which is almost frozen in comoving coordinates, that is expanding, but it has, most importantly, it has order 1 inhomogeneities at scales which are the typical size of the horizon when the axion field destroys the network, which is when the axion field starts to oscillate around the minimum. So these inhomogeneities here will collapse very soon around matter radiation equality, leading to these small mass mini clusters of masses of order 10 to the minus 12 solar masses that are going to be the smoking gun of this scenario, I think. So axions radiated from topological defects. So in this scenario, the dark matter is composed of axions, and there are different sources of axions in this scenario. First of all, we have a network of global cosmic strings that is in the scaling regime for many eFols of the expansion of the universe. Now, these global cosmic strings are just essentially, they have energy in gradients of the axion field. So they have a lot of energy, but this energy is stored in the gradients of the axion field, which in principle would diverge around the strings, around the global strings. So they are string-like regions where there's a huge amount of gradient energy of the axion field. And these cosmic strings, so this huge energy drives the strings to the Hasse dynamics such that the length of the string tends to be minimal, or has to decrease, right? Because so this is the dynamics of the strings tends to make the string length smaller, and this is by, for instance, these strings, they form typically loops of all sizes. So loops will tend to decrease in size, and sometimes long strings, they can reconnect. and then form kinks that or form smaller loops that can collapse faster. And also some the strings, if they are bent, they can oscillate. These oscillations are damped. In all this dynamics, the strings can radiate axions, can radiate axion waves, not axion gradients, but axion waves that will behave so that then will be the dark matter. So the story of this scenario is how the energy of the huge energy that is stored in the strings can be transferred into axion waves. Okay. Well, so during the scaling, yeah, there is some action that goes from the strings to the axions. Then at the QCD epoch, the axions that have been created in this epoch are going to be processed by nonlinearities, and also at the same time, the zero modes of the axion field will start to oscillate. There will be the misalignment regions. And later we have the free streaming, and the axion number is conserved. Now, when we calculate the axions that are radiated by strings, the quantity that is most important is what we call the string spectrum. So it's how are the axions radiated by the strings distributed in momentum, okay, or in energy. And depending on how this distribution is done, we can have a huge amount of axion dark matter or a very small amount of axion dark matter. The spectrum radiated by axions, we all more or less agree, it has a cutoff, an infrared cutoff at the causal horizon. So strings cannot produce axions which are of energies which are smaller than the Hubble rate, because there's no time for these axions to move and to contribute to the energy density. And it has ultraviolet cutoff at a scale FFA, which is the typical thickness of the string core. So also, and we all see this type of spectrum in our simulations. Now the simplest assumption, and we have no better ansatz for the continuation of this. So for the emission spectrum between these two cutoffs, that a power law, and actually because the system doesn't have other scale, and this is actually what we observe in simulations, at least to some accuracy, we see that there's a power law between these two cutoffs, but the index of this power law of the emission of axions is extremely important, because if axions are very if this value of Q, the index of the power law, is much larger than 1. This means that most of the axions are emitted at low energies. So when you put a lot of energy into the low energy part of the spectrum, you are putting a lot of axions, right? And then each of these axions is going to contribute to the dark matter of the universe with the amount of equal to the mass, right? So when Q is much larger than 1, you will produce a lot of non-relativistic axions. And if Q is much smaller than 1, this means that you are putting all the energy into a few highly relativistic axions, and then you will create less dark matter. Very good. Now, so how can we calculate this spectrum? So in principle, one can build an effective field theory of infinitely, well, of strings. The Nambu-Koto theory, and one can couple it to an axion using the Kalb-Ramond field. And this, so this is a theory in which many people have studied analytically. So the radiation of axions, and when the string moves. So for instance, when a loop collapses, or when a string that has been perturbed sinusoidally oscillates around the position of equilibrium. So one can calculate the axions emitted in these cases, with the problem that is very complicated to take into account the back reaction of the axion emission into the motion of the string when the emission is large. Here, it's interesting that in this theory one can see that the string couples to the axion field with a coupling that is inversely proportional to the logarithm of one particular logarithm, which is the logarithm that controls here the dynamics. Okay, in order to understand this log, let me just show you over here that so that the energy density of the string decreases as 1/r, where r is the distance to the string. And this 1/r is simply because the axion field goes from 0 to 2 pi around the string, right? So this means that close to the string, the axion field will be 0 and 2 pi. We'll be taking all values between 0 and 2 pi at one point, essentially, right? And this has infinite gradient energy. So this is only just telling us that exactly the gradient of an axion field that is pointing in also this turning 2 pi around the string goes like 1/r squared. And therefore, if you integrate it until a given radius far from the string, you get an energy per unit length, which is proportional to which is divergent. Huh? So you get the integral is proportional to the maximum radius that you integrate divided by the minimum radius that you integrate. Now the minimum radius is naturally supplied by the core size. That is an ultraviolet quantity that has to do with Fa. But the maximum radius depends on the dynamics that you are considering. And typically in our networks is the distance to the nearby string where the gradients change. These are max, therefore, is typically the distance to another string and is of the size of the horizon, which is 1/the Hubble rate. So this log, whenever you see this log in my slides, is going to be the log of a huge quantity, which is Fa divided by h. So one can show that actually in the effective theory, the coupling of axions to the string is 1/log. So this means that when log is very large, so with the so the axions kind of decouple from the strings, and global strings, which is how these strings that are dressed with an axion field, they should behave a little bit like local strings, which are easier to understand. So one can use this effective theory in some cases, but also one can actually do numerical simulations, which are the techniques that we are at the end we rely on. And there are different ultraviolet theories that give you the same infrared theory, which is a string coupled to an axion field, right? The simplest of them is using a complex scalar field. Now, the problem of these simulations is the ratio of Fa divided by h, which is the ratio of the scale, the ultraviolet scale, to the distance between strings, is of the order of 10 to the 30 at the end of our simulations. This is only a log of 70. So this means energies. So we are off. 10 to the 30 is a quantity that we cannot simulate. We cannot do simulations with this dynamical range. Okay. For instance, if we use simulations with regular grids, Cartesian grids, the maximum number of points that we have managed to put in one direction is 10 to the 4. This corresponds to a log of order 9. So we are off by 10 to the 26 orders of magnitude in representing the gradients of the axion field. But the energy of the string, we are only off by a factor of 6, right? Because we can, energy-wise, we can have strings that have energy that have a tension which is 9 instead of 70. It's a factor of 6, 7, 8. Now, so the maximum regular grid that we have managed to simulate is 10 to the 4, and I will show you some results of this. But in principle, one can do adaptive mesh refinement around the strings. So one can use the RAM of the supercomputers and supercomputing time only when we need this resolution. And this, if you just do some easy estimate, one can calculate that if you can if you have a grid of 10 to the 4, you probably can also use 13 levels of refinement, each of them being a factor of 2 smaller than the previous. And this would allow you to simulate until 10 to the 18. So this is the absolute maximum, stretching all the RAM and the techniques to the maximum. Most likely, this will not be possible, but this would be the maximum. And next week, we will have our colleagues, our American colleagues that have done these simulations, AMR simulations. We can discuss about them, about whether this is possible or not. So, so what happens when we do the simulations? Well, I want to talk to you about the simulations we have been doing, which are very similar to the ones that Ed and Bilador and Giovanni have been doing. So first of all, the most important thing is that the energy of the strings can be calculated, and is typically limited essentially by causality. So we have essentially one string per causal horizon. And this gives this string causal horizon gives you an average density, which is given by this quantity, and we can find we can find this parameter of order 1 in our simulations, and we see that this parameter of order 1 is not constant, but is slowly increasing in our simulations as the log increases. So this is something very interesting, because this is also so in the previous literature, one was assuming that this would be just a constant for all values of log. But we can see that regardless of the initial conditions that we use, the system tends to kind of an attractor solution in which chi is of order 1, but is slowly increasing. Now, if you take this energy of the strings and you calculate the time derivative, this is the energy loss that the strings are, so is the energy that the network of strings losing per unit time. And this is the energy that is available for the to produce axions. Okay, so the energy lost of the network is the production of axions between the strings. So you can estimate with this that the energy density in axions has to be of this order, which is 8 pi this parameter times the log times FA squared h squared. And this FA squared h squared is the typical value that is that the energy from the actions from the misalignment are going to have. So parametrically, this energy density is larger than the misalignment energy by a factor which is high log. And log can be 70, and high, if you extrapolate this to the physical values of 60 or 70, gives you something like a value of 15. So this potentially, this can be a factor of 10 to the 3 or so larger than the misalignment energy. So you could have more, something like 1,000 times more axions than those predicted by simply putting random initial conditions without strings. Now the problem is, how is this energy distributed in momenta? And so with our numerical simulations and the numerical simulations of the Americans and Giovanni and Ed, so we have put up together this plot in which we show the value of Q as a function of log, and the results of Gorgetto et al. So you show very clearly that the value of Q is smaller than 1, but as you increase the value of the log, it's actually the value of Q is increasing. And this is, I think this was interpreted by them as a slow approach to the result of the effective field theory, in which the strings are known to radiate with a value of Q which is larger than 1. Exactly. So this would be the trend. We have redone their calculations, and we have improved on similar things that I will tell you a little bit more later. And our blue calculation shows precisely the same trend. So also Q smaller than 1 at the beginning of our simulations when the log is not so large, and then slowly increasing. Finally, our results converge with theirs, and then continue growing. In particular, they also go over Q equals 1. Although at this, exactly. And then we have the simulations of the Americans. Actually, I said simulations, but it's only one. So they did just one simulation and they use adaptive mesh refinement to resolve the dynamics of the strings very, very well. But they present us with these results, which have relatively large errors at small log, and then they almost don't change and don't depend on log. And this is very nasty because the extra, so you see Q is more than 1 for most of our simulations. This is the first thing you see. But now if you want to extrapolate to large log, which is the physical value where we want to have our simulations, this extrapolation depends not only on the large log points, but also depends on what you have before, right? Because you want to see the trend, right? So now if you have a flat trend, you are going to extrapolate to Q equals 1. If you have a growing trend, you are going to extrapolate to Q larger than 1. There's a controversy here, right? So actually the American group would say that the Q is equal 1 with some error, and Italians or this naive extrapolation would say Q is around 5. The definition of Q? The definition of Q is this. The derivative of the axion energy with respect to time as a function of momentum, right? So this is the energy density of axions, so the spectrum of axions, right? Time derivative is a power law. So the index of this power law is Q.
Two questions. One is, so you see that the trend is more steep than the one that the other European group.
Yeah.
So meaning that it matters more the axion in the screen. Yes.
Mm-hmm.
Okay. So it's not the same slope that you're finding.
The slope of the Italians and yeah.
Or it's more steep, right?
This is slightly more steep. Yeah.
But the slightly means.
But
more impact for the other.
Not really. So once, because the extrapolation goes around to Q equals 5 or so, and for Q equals 5 or 6, the result is almost independent on Q. So once you go above Q equals 1 point something, the result stabilizes.
And in the second, the energy loss due to the network is going to the axion. What happens with the variables? So you can have some energy there. I guess in your model you see that right there.
Yeah. So there's always some production of radial modes, and so in the simulation is quite significant. It's relatively significant. One can see that it decreases in some cases with so the ratio of the production into axions and into radial modes decreases. So the radial modes are being less and less produced. There's always some creation of radial modes. And what happens with the radial modes is that they decay into axions. In reality, they will end up decaying into axions and producing some peak at half the radial mode mass. And only at physical logs, this is completely negligible. So this is of yeah.
But remember that the number of strings right?
Yes.
So what's the number that you get for
this is 15. So at the end of our simulations, we have 1 point something, 1.2, and then going to the value of 60 or 70, you get 15. 15 is a very interesting number. This is also the density that one gets in local string simulations, yeah. So it's not any arbitrary value. So it agrees very well with the general. Yeah, but do you get it before? Right? Well, not in numerical simulations of resolving the cores and so on, but in numerical simulations of string-like objects, really one-dimensional objects evolving, not a field. So there are field simulations in which you simulate here the axion field and the radial field, but you can also simulate the Nambu-Goto action, right? Which will be only one-dimensional objects. And these simulations you see there, 15.
Is that a coincidence, or is that actually flat line?
From this point of view, it's a coincidence. because yeah, we extrapolate with a straight line. So what is that? It depends. In this simulation, we went to, so we normally, well, I like to quantify this by the value of the radial mass multiplied by the discretization or the delta x, right? So and normally, I think for our strongest, most ambitious simulations, we went to 1.5 at the end of the simulation. But if you want to be sure that they are correctly describing the spectrum, you have to stay below 0.5. This value is decreasing it's increasing when the simulation increases, because the axion mass is constant, but the universe is expanding. So this delta x physically is expanding. So this quantity is growing, right? I just wanted to say a few words about whether there is a controversy or not. So first of all, we find that the results of the Americans and ours are different, and they might be different for a number of reasons. First of all, if you look at the density of strings, so the high parameter, the simulations of our definition of the attractor implies a density which is larger than the initial conditions that Bushman et al. Used. And you find, so when we study the value of Q as a function of the different density of the networks, we find that when the networks are underdense, so when they have less strings than the attractor, the spectral index is larger. And this can be understood as, I mean, when you have less, so when you have more strings, if you want, so that you have more interconnections, you have more loops, you have more small scale structure, and you have to produce, exactly. And then this tends to make Q larger because you enhance ultraviolet production. Under dense networks means that you have less features at small scales, and you get large values. So this is one of the effects, and why the simulations of Bushman et al. Can find a value of Q which is larger than 1, which is larger than ours, sorry, at logs of order 6 up to 7. And this cannot explain the larger values or different, so the difference at logs larger than 7, at least from our study, but this can tell you something about the trend, right? Because for the extrapolation, you need values also below log 7. So another feature that is very interesting is that when you study the evolution of one mode of the axion field, so you see that you see axion oscillations. So you see oscillations of this mode. So the evolution of the mode is not a straight line. So depending on how you calculate the numerical derivative, you can get very crazy results. For instance, imagine that this is the quantity that I have to calculate the derivative, right? So if I calculate instantaneous derivative of an oscillating function, I can get negative values, positive values, I can get anything, right? So, what the Italians did was just to take a relatively large value, right? Which is delta log of one quarter or so, which is typically is a nice separation. But nevertheless, you can, because of this oscillation, you can get a bias, right? And the Americans did the same. Now, what we do in our study is actually find a fitting function, and then that smoothly interpolates and averages over these these oscillations to make sure that we get the correct trend. But if you don't do it, you can get a power spectrum that is very strongly oscillating, and then you have to smooth this, and this can introduce a bias that can change the value of Q significantly, particularly depending on the cutoff that in which you use to calculate Q. Yep.
When you say axion field oscillation, what's oscillating? What are we?
So these are oscillations on the power spectrum of the axions, right? So you have this. You have to evaluate this quantity, the spectrum of axions, and then you have to, and this is typically calculated as the value of Fourier transform of one mode of the axion field velocity squared. So you have the axion, the time derivative of the axion. You calculate a Fourier transform. You bin it, so you average it over directions, and you bin it in momenta. But then exactly, and this is this quantity that you saw before. And these oscillations are because you have in one bin you have different modes, and there's bitting of these oscillations, and also because when the axion mass crosses twice the half of the axion mass, there's some production of axion, some coherent production, parametric resonant production of axions from axions, and it's coherent. So all these modes are produced in phase. Very good. Then, depending on how you discretize the Laplacian in the equations of motion, you get that the axions can propagate closer to the speed of light, or they are at high momenta. They have smaller group velocities. So Bushman et al., so the American simulation, used one neighbor to calculate the Laplacian, and we have done the study of different simulations using different neighbors. And we find that at least one has to use two neighbors. Well, actually, this was found already by the Italian group, but we see a small difference also for 3 and 4 neighbors. So actually, one would in principle should use 3 neighbors to see a convergence in this in our results. And you see when you use one neighbor, the value of Q tends to be larger. What is the x-axis? The value of log. So the hierarchy between the core and the distance, which is also a proxy for time of simulation. And then finally, you have the core resolution, which can be extremely important. You have here simulations at the same time with different values with different number of points different number of points per core, right? So the value, and you see that this is essentially the value of the differential spectrum, so the derivative of this. And here you have the ratio between the value with a particular number of points divided by the value of 0.3, which would correspond to 7 or more than 7 points per core. And you see that there's very good convergence once MRA, which is this quantity here, is smaller than 0.5, at least at these values. But if you abuse the resolution, if you put too few points, you are going to underestimate the spectrum, and also with a particular dependence on the momentum, right? And this dependence on the momentum ends up producing more infrared axions and less ultraviolet. So this also making Q larger. So yeah, so I think in our paper we are concluding that these 4 effects make the results of Bushman et al. More compatible with the results of the Italians in our simulations. So at least this explains why we are getting something so different, right? And we have to say, so both approaches have different extrapolation properties. So one thing is with Q equals 1, if one calculates the number of axions from the spectrum, one gets this number and the axion dark matter mass of the order of 100 microelectron volt. But if one uses the spectrum that rises with log, one obtains essentially 1 order of magnitude more axions, and 2 orders of magnitude more axions, almost 1 order of magnitude more axion mass. And it's very interesting that there's this very extreme. So these are our conclusions. I cannot tell you what is the right extrapolation. I don't know whether a straight line is the right extrapolation, but at least I can tell you that I think in our opinion, all the numerical results at the moment are compatible with each other. It's only the interpretation that is different. Yeah, so in this respect, exploring really the values of log around 10 with very good numerical resolution would be crucial, because we could see really if there's something going on around Q equals 1. And yeah, in principle, we have a clear linear trend, but could be that the attractor, this attractor solution is a way to approach the Q equals 1 result. If there's something special about Q equals 1, and I think we will hear some ideas and some, so the Americans have some reasoning that they think that Q should be 1. Only the Americans, only Bushman et al. Could be some systematic, could have some systematics, yeah. So we are starting to do these numerical simulations, so we have been doing that for some time, and there's a lot of systematics to care about. And they are also running more systematic checks. I think we will hear much more about this next week, also in the talk of Ed, but not AMR, sorry, but maybe more about this topic. But I wanted to tell you, to give you something more, is that in principle, one can simulate, we can also calculate the spectrum of cosmic strings, not from a simple theory with a complex scalar field, but one can do more complicated theories, like the one proposed by Guy Moore, in which one has two complex scalar fields and one gauge field. And with this construction, you can get axion field that is very weakly coupled to the strings. Effectively 1/, so with a coupling which is 1 divided by the right value of the log. So this is an effective way of getting a theory that is very weakly coupled to the strings, which is what the real cosmic strings are in the QCD axion case are suffering, right? And so he didn't provide any study of the spectrum of axions radiated from the strings, but we have recently done it, and we find something very interesting. So we find that the spectrum is not larger than Q equals 1, so it's more or less consistent with Q equals 1. Of course, we don't have a huge range of so these simulations are more complicated than the previous ones, so we cannot go to the same value of the hierarchy between the core and the distance. So this value of the log here is really the log of the hierarchy between core and distance between strings, but it's not the effective log with which the axion couples to the string, which is in this case of the order of 60. So we are in the physical point. But it's very interesting that with these simulations, the ultraviolet physics is so strong that doesn't allow Q to grow larger than 1 or so. There's a lot of things going on here, much more nasty things happening in the ultraviolet, but the infrared part is relatively simple, and it shows Q equals 1. And there's another possible hint that Q is equal 1, which will appear in our paper, which is another method of calculating this Q, in which we don't calculate this spectrum and fit the value of Q directly, but we actually calculate this spectrum in the infrared, and we calculate the overall amount of axions emitted, and then we say, okay, the spectrum has to be the infrared calculated part, and it has to be, when we integrate it with a power law, it has to give us the total amount of axions emitted, and then we can extract the value of Q that we would get for that. And if we do that, we obtain this final result here, which I didn't describe, this orange, which also shows a rising value of Q, but finally, when Q becomes of order 1, it plateaus and stops growing. The difference between these two methods, we believe they might be attributable to discretization effects, but we are finalizing our study. Yeah.
Remember, in this case, you are much more sensitive now to final quantum because the density now is dominated by the Redondo. So how much?
Actually, we are computing the energy density.
The energy.
Yeah, because well, at the end is this. So we are using the infrared part. So the infrared is crucial. Yeah. So we are using the infrared part because we want to have exactly that part under control. The observable are the infrared part of the radiation spectrum. So if the infrared part is the low momentum. Here. So this part, the infrared peak. Yeah. Exactly. We use this from numerical simulations, and then we attach. So we just decide that from certain momentum on, there's going to be a power law with a cutoff, and the cutoff we extract it also from the data. And then we feed the power law to match the integrated part, the integrated axion energy, which we have found that is less sensitive to discretization effects. So we see that the integrated, so that the momentum, so the time derivative of this quantity integrated over the momentum, and extrapolated to the continuum as the whole spectrum. So we have the low part and then the full integral. So in a sense, we are assuming that discretization effects might move some axions left and down in the ultraviolet. So, and actually we see that there are some distortions there in the ultraviolet, mostly. Yeah, and so this is why we do this, but we don't have any reason why this method should work better. So this is one of the problems. This is just another way of calculating the same that seems to be less sensitive to discretization effects. And in our results, because we want to reach more or less the same values that the Americans reached, which is almost 859. So we have to be a bit aggressive. So we have to deal with discretization effects. So the philosophy of the Americans is let's try to resolve the strings with a lot of points, right? And our philosophy is let's try to understand discretization effects so that we can go a little bit farther. We can remove them. No, so we start with a field with a complex scalar field whose modes are exponentially suppressed above a certain length scale, and this length scale is calculated such that we are in the attractor. So we try different lengths, and then we study which one is what corresponds to the attractor. And the attractor we define it by the suction emission. So by the attractor in suction emission, not by the position of the. Mm-hmm. Yeah. Mm-hmm. Yeah. So what we did was so at the beginning of the evolution, we have a small period of PRS, the expansion of the universe, in which the coupling to the quartic coupling is not constant, but is decreasing. So we do fat strings at the beginning of the simulation. So we have tested many different things to see what are the initial conditions that give us more stability or less action emission, and those were the best. We can elaborate more on this. I can show you more plots, but I don't have them here, unfortunately. But we decided not to use. So the Americans, they use something completely different. They just say, okay, we are going to do a phase transition, a particular phase transition with some parameters, and they don't test different parameters. They don't show the sensitivity to initial conditions or anything like this. They say that the final results should not change very much. Yeah, no, and I think so that the sensitivity to initial conditions should be small at the final stages of the simulation. So where log is equal to 8.5 or 9, it should be small. But since you are doing an extrapolation based also on previous previous logs, and we can see that there is some sensitivity to initial conditions. So then I think we look forward to their study.
Let's say there's this problem that the extension
Mhm.
So now I was wondering whether they can now consider the integral
Mhm.
to get the solution to other modes that are kept emitting by the string.
So what we do is, so when you look at, so we look at the evolution of one mode with many time points, right? And then we fit a function, and then so the residual is further filtered. So we filter all frequencies that are above the characteristic axion mass, axion momentum in that frequency. So we remove for sure axion, so effects of axions above the momentum bin. But yeah, so it might be that this, but okay, maybe we have to discuss a little bit more about this. Yeah, so yeah, so but I'm done. So so let me just publicize. I think Ed is going to, so during Ed's talk we can talk much more about this systematics and all these things. And I just wanted to flash that when we talk about cosmic strings, there are other things that we have to discuss eventually, like the fact that these strings can be superconducting, that we are not including gravity in the simulations. There can be fermionic zero modes of other fields. There are people that say that one can have black hole production in some of these scenarios. And then there's n larger than one scenario that can be very interesting. So, but what is the smoking gun of this scenario? Is actually the presence of these small mass mini clusters. And I think they have very interesting implications for direct and indirect detection. In the direct detection frontline, we have the fact that if most of the axion mass of the universe, all the axions are in mini clusters, we might not have enough mass available for our experiments here on Earth, because it's extremely complicated, it's extremely difficult that we will cross one of these mini clusters. And so we need to know the small scale distribution of dark matter as Earth's position, and we are going to be very sensitive to it. But in the indirect detection forefront, we can have that these small mini clusters could lead to some observable consequences like femto-pico micro lensing or caustic lensing. We could have the formation of stars inside of these mini clusters, and these axion stars could be unstable and produce relativistic axions or radio waves. And we could have also sometimes these mini clusters, they just fall into a neutron star or a heavy magnetized object, and then convert massively into radio waves. And we suddenly have something like a radio burst, something like this we could detect. So these things would be symptoms that we might be in this post-inflationary scenario. And if Giovanni wants to take the stage, he will tell you more about these mini clusters.
Very well. Yeah, so in the interest of time, I'll try to keep it quick and just maybe flash out what is the state of the art for mini clusters and what are the problems. So yeah, so Javier has spent a lot of time talking about this controversy on the contribution from strings, and that's actually very important because the spectral index Q will not only determine how many axions are produced, and therefore if you assume that they are 100% of the dark matter, what is the axion mass? But it will also, I will try to argue that they also have implication on the spatial distribution of axions, which are affecting the potential observables, so direct detection or indirect detection. So what are mini classes? Mini classes are essentially gravitationally bound objects that can form even before matter radiation equality. That is because the network of strings and domain walls can leave some large over densities at the QCD epoch. So this large over density will collapse due to gravity, and this, as I said, can happen before matter radiation equality. And therefore, the story of mini classes will start in what I call the early universe in these mini cluster seeds, which happens around the QCD phase transition. So all the uncertainties that you have on the string emission will therefore be propagated on the late part of the universe if you want to study the mini classes. So you need to do some extrapolation for this reason. And what I'm showing now is how we could model the mini classes, but however, without doing this sort of extrapolation, because we wanted to do a numerical, full numerical study in a cosmological timeline. So what I call the early universe is this part where there's the domain wall decay and the Axions, so around the QCD phase transition. So I just quickly show what actually happens qualitatively. So you have a string network that is interacting, and as when the axion mass turns on because of the QCD potential, domain wall forms and they will collapse if the system is unstable. And you're left with axions produced by wall decay. And at the last time, you can see that the grid is kind of frozen. Modes are not moving much because most of the axions are not relativistic. So as I said, this type of simulation that is essentially what has been done a few years by Javier and collaborators has this uncertainty, has this problem that the spectral index was more than one, because that's what you actually see in the simulation. So in principle, you would need extrapolation, but if you continue the system with this numerical configuration, you have to know that it might not be correct because you need to extrapolate. So in particular, for example, if you have the Q is larger than 1, the wall decay might be delayed in time, and then therefore will have some phenomenological consequences. So quantitatively, what we want to look at, for example, is the power spectrum in the energy density in Axions. And so what we see in the simulations, the video I've just showed, it would correspond to the black line at the end of the simulation, somewhere in a linear regime. And you can see that there's quite a large fluctuation. Large fluctuations, large correlations on scales which are 10 times this one of our L1. So L1 is the causal horizon at the time when the axion mass is comparable to the Hubble parameters and when the axions start oscillating. So that will tell you that mini cluster will form on those scales. But that's assuming this Q is more than 1. If you extrapolate and you take, for example, Q equal 2 or larger than 2, doesn't really matter what the number of this Q is, but what you can see that the spectrum is shifted to to larger momenta. So what you expect is essentially that if Q is larger than 2, the mini cluster will have much smaller mass because they will form on smaller scales. So I didn't have to. Yeah. The shape is quite non-trivial because if you had just a misalignment, you would see some sort of Gaussian lump on the scale comparable to 1/L1, and this peak is due to domain wall decay. On larger scales, in principle, so these power spectra are calculated in the linear regime. So we apply an adiabatic approximation at the end of the simulation. So we kill off all the nonlinearities, all the self interaction, which are actually only affecting the very, very small scales. So essentially, you might be wrong. You might be wrong on the tail here. You might be because you're not describing very well the small scales, because you also have discretization effects. But up to these kind of scales, you're kind of certain that you have a sort of like a peak. So this time is right after the QCD phase transition. So you might say like 100 MeV or so in temperature. The problem is that in the simulation we start around like 1 GeV when the axion field started oscillating, but we cannot really see the whole phase transition. So the mass is growing until until the QCD phase transition temperature, the critical temperature, sorry. But we cannot actually simulate until that point. So we have to stop our simulation and then kill all the nonlinearities with an adiabatic approximation, which is a good approximation for most of the simulation, because only at the very small scales we have this self-interaction happening. Yeah, so okay, so the main point is that the shape might not be the same in the QD=2, but it's definitely shifted to large momenta. So you will have mini cluster mass, mini cluster forming at smaller scales. So the phenomenology will change because of that. Yeah, so we also have some uncertainties in this small case, as I was mentioning, due to these axitons. So axitons are locations in the axion field where they have this large field value. If you have a large field value, then you're looking at the top of this periodic potential where the self-interaction is actually playing a role. So you have nonlinear dynamics that you cannot neglect. So these axitons, due to the fact that the axion mass is growing very fast and you have large field values, they tend to collapse. This self-interaction is attractive, so it's like gravity. And so you have these axons which tend to collapse, and what we see in the simulation is that they produce relativistic axion waves. And they're quite resilient in the simulation. We don't see them disappearing after the final simulation time. As I said, we have to apply some adiabatic approximation that removes them at the end of the simulation. So that is a sort of a problem only for the spatial distribution, because if you care about the axion abundance, they don't really affect much of the energy density budget, because they're very small localized regions. So the number density of axions should not be affected by what happens to these axitons. But the spatial distribution will be affected. In particular, we're looking at parts of the axion field that will seed the largest of the densities. So largest of the density will be the first one to collapse into mini clusters. So they will affect the spatial distributions on the very small scales. So let me go into the late universe, so we can continue the simulation numerically. We can actually take the configuration at the final simulation time at the QCD phase transition. We can apply some free streaming, and until a redshift of around 10⁶. So way before matter radiation equality, the first of the density will start collapsing due to gravity. And what is interesting is here that we can continue the simulation with n-body methods rather than a lattice method. And that is because any wave-like effect that you would have to resolve with some lattice treatment happens at very small scales, which is even smaller than what we can actually resolve. So we switch to n-body particles, and we just have collisionless dark matter, essentially, which is convenient computationally. So this has been out for the first time a few years ago by Javier and collaborators. So they looked at this n-body simulation of mini cluster that collapse due to gravity, and then they merge and form they merge into larger mini cluster halos. So what they've done very quickly is that they found the halo mass function, so how many mini cluster per mass. So you can see that you have two cutoffs. The cutoff on the large mass depends on it will tell you what is the maximum mass that you can get from merging of mini clusters. They looked at the density profile, and they find quite a good agreement with the NFW profile. But what is also interesting is that they calculate how many axions are inside these mini clusters, and they find that roughly up to 80%, close to 80% of the axions are inside these bound objects. So, yeah, 80. What did I say? Okay, sorry, 80. Yeah. So as you can see here, from the initial redshift of 10⁶ up until a redshift of 100, they see that the number of axions start to grow inside a mini cluster starts to grow, and almost plateaus to close to 80%. So this is kind of important, because if all the axions are inside the mini clusters, and an encounter with a mini cluster is quite rare, you might argue that there's no axions outside of them to be detected on Earth. Before, well, it's essentially zero, and this is equality It sort of depends on how you define a mini cluster, but you get up to like 40%. Yeah. No, all sizes of mini classes are included because in the
you say that there's a process like factor 6,
so there's this sort of two types of populations of mini classes. The first one that collapse are like a 10 to the 6 or so, and they are quite they form from larger densities, and then some of them merge into larger ones through hierarchical merging, but some of them stay isolated. And that's actually quite important because the isolated ones might have a power law profile. Power law profile can give you microlensing, can give you high chance of survival when around the galaxy. So it's quite important to understand that if these isolated mini classes are still around, or if they merge into a less dense object.
You already said that, sorry, how you stitch these two things because it's not these Axions, right? Okay, first question, why is it so resilient? Not even
So the point is that they're in a regime where self-interaction dominates because of the large field values. So they tend to collapse and disappear by emitting relativistic waves. But then these relativistic waves do not free stream so much because at the same time, the axion mass is growing. So they get slower and slower. So a collapse of one accident is likely to seed another accident because the field values stay locally are still large, right? No. They will. I presume that they will disappear as soon as the axion mass stops growing.
So you can make a 2% of the 10% of the actions were located there, but the rest stays there. So one collapse, it's not able to destroy the action. So one collapse several times, then you typically see that the action relax a bit. But if the density that has been left over is always so critical. So that there's another reason that is close by is creating some energy we can collapse rates. And this actually can sleep always in items. So these collapse they come to life very often.
And they come to life with as smaller scales because the mass has grown and the size is the inverse of the mass, axion mass.
Okay, but so they use like okay, yes. Yeah. It's very weird that it needs so long, right?
They are fast,
but they're not the same ones. They're not the same ones. Yeah.
And so are you stitched up here to the endpoint?
No, because that happens at the QCV phase transition. Then we have a linear approximation. We essentially artificially remove them. So
how you put the initial condition in your endpoint?
Yeah. So we take the configuration of the final or the early universe simulation. We have the accidents at the end because the mass is still growing. So we have to stop at some point because they reach the core of the accidents is the discretization. So you cannot trust what happens after that. So we still have them. We apply a linear approximation. We kills them off. It's a WKB approximation. The WKB approximation is done until 10 to the 6, which is just free streaming. You can do it analytically. And then so you still have your grid, and then you create a configuration of particles from there based on the energy density. You can do it in many ways. You can either put more particles in over dense region or put a particle mass larger there. That's it. Yeah.
What we expect is that the action will continue very fast for a longer time than we allow them. But then after physically to continue to collapse and make the action, the central energy will continue increasing. But then at some point, it will explode the last time and then will freeze. So what we do is just starting with streaming with the accidents which are with the density which is smaller. We started before. So the large scale structure is going to change, but the small scale structure can be.
Yeah, so in the end, what this means is that on the small scales, we cannot really trust the substructure, and that is a problem because that means that you cannot resolve very well the mini classes on those scales.
The check is properly okay, also not very similar.
Yeah, the main, I think the difference is that the mass is also growing as well. It's not constant. But as soon as the critical temperature will kill the axial mass growth, and then they'll disappear. Okay, so the embodied simulation also has to stop at some point, unfortunately, around the redshift of 100, and that is because even the box size scales, so the largest scales that you have in the box, they go nonlinear because we're talking about one parsec or so. So at Z of 100, that scale starts to become nonlinear. This is unfortunate because this is very early in the universe for an astronomer, because the galaxy hasn't formed yet, so we don't have a way to model the small scale dynamics while the galaxy is forming. While on larger scales, you should expect that the structure formation happens in the same way as lambda CDM. That is because on those scales, the adiabatic power spectrum will dominate. So the power spectrum that will give you the mini classes is isocurvature power spectrum. Okay, so another thing which could be interesting for indirect detection is microlensing, and I'll just flash this very quickly. Essentially, we want to understand if microlensing is ruled out by what we find in the mini cluster simulation. And that it turns out that for this kind of configuration, so bearing in mind that the initial condition might be affected by the fact that the string spectrum was not the correct one. So Ellis and collaborators find a very tiny window of possible candidates, many cluster candidates that could give you microlensing events. But if Q is larger than 2, for example, then as I said, the mini cluster mass might be much smaller, and you might not reach this threshold, and you might not have microlensing events. So microlensing doesn't seem to be a viable option to find mini clusters. That's the main take. So after Z of 100 to Z of 0, you should understand, we want to understand if these mini clusters survive or not, because as the galaxy form, they will rotate around the center of the galaxy, and there might be strips because of tidal interaction. So there's been quite a few advantages on this. And essentially, the bottom line, I'll just try to summarize very quickly, is that the survival probability of these mini classes, if they survive or not, due to these encounters with stars or due to the tidal forces of the Milky Way, highly depends on the density profile, which we do not resolve to the smaller scales. So this is quite, that is to say that we need to run more simulations. We need to have better resolution. We have to have a way to understand what is the density profile of these mini classes, to understand if they survive, and if because the survival is crucial for direct detection, because if they all survive and they have most of the axions, then outside of them there's few energy density, and the signal then a direct detection experiment can have will be suppressed. Yeah, so I'll try to. How much time do we think? I have 2. Yeah. Okay. I actually wanted to talk. I actually wanted to say one last thing. One last thing is that so what we try to do recently is to actually compute what is the energy density outside of these mini clusters. So as you can see, these yellow to red regions are the mini clusters and the mini cluster halos. But as you can see, most of the volume is dominated by what we call mini voids, because they're cosmic voids, but on very small scales, the subgalactic scales. So what we want to estimate is the energy and how much volume they occupy. So this is strictly for direct detection experiments. We want to know if can direct selection experiments, these cavities, can they see the axion in the post-inflationary scenario? Because if most of the axion is in these bound objects, and these bound objects have no chance of encountering or passing through Earth, then what is the actual energy density that we have to detect? So we estimate that roughly at last simulation time, 80% of the volume is dominated by these voids, and they typically have, as you can see from here, a typical energy density which is like 8 to 9% of the average value, and it seems to be reaching a constant, which is it's kind of interesting because that lets us put a lower bound. Because what happens is that if the void energy is constant, and then it can only increase after Z of 100 if the mini classes will disrupt and spill some axions inside these empty regions. So that's let us put a lower bound on the haloscope plot. So you can see here is the famous coupling versus mass plot. We just shrink into the tiny window, which might give you 100% of the dark matter. And if our results on the voids are correct, as a lower bound, you should, just for a second, you should move all the haloscope bounds by a factor of 3 to 4, which is, that is to say, there's less energy that what they assume there is. And so they might not be probing what they claim they are. So I'm not saying this is the real thing, because this is just a lower bound. This is, you wanted to estimate how bad it could get for them, which is not that bad, I would say. Yeah, that's why it's a lower bound, because the disruption mini cluster can only increase the energy density. That is the argument. Yeah. Yeah. That's right. That's a good point. So the mini cluster occupy less than 1% of the volume. So the remaining 20% that you have there is sort of filament-like structure, or out on the outskirts of mini cluster, which is average density. Average, yeah.
We're saying that still the majority of the
Most of the energy is inside the 1% of the volume. 80%. So the bound fraction is how much energy density there is in mini clusters, and it goes to 80%, and that has to be compared with the energy density in the voids, which is actually decreasing. So these two, I mean, energy should be conserved. So yeah. The typical size of the voids is, okay. Sorry. So the box, as you can see, this is 0.1 parsec. Our box is less than 1 parsec. So a typical void might have at most 0.1 parsec or so. Yeah, which is much larger than a typical mini cluster. Yeah, that's sort of comparable to the causal horizon and the QCD.
Experiments in many places in different regions of the universe. Or inflation.
Yes, I think the point is we want to understand how much density there is in streams. So if the mini clusters are disrupted, how much elongated are these streams? What is the stream density on the solar neighborhood? Because that will tell you how much of this can increase. But yeah, I mean, yeah, that would be ideal. So as I said, this is what we try to understand, and these haloscopes, if we trust our results on the voids, are not actually probing the QCD axion line anymore. So yeah, not a great news for the experimental collaborations, but this is supposed to be a lower bound. So this is how bad it could get, according to our estimation. Yeah, I think we saturated the the amount of content for today.
Okay, then, I guess.
Okay, the type of question was over already while Javier was. But this is important, I think we can see after the, very interesting, like, for the work of interest. Or for question, you can speak for it. Was uncomfortable.
Yeah, because some of the overdensity are larger than order 1, so like up to like 30 or so. So an order 1 overdensity, if delta would be the overdensity parameter would be 1, that would collapse at equality around that factor 1 order. So you have an overdensity of 100, then you would, yeah. Yeah, in principle, yes, but we don't have our overdensity larger than 1,000, so we don't have to stop before than 10 to the 6.
The question was flashed because it's true that
Well, you would have to keep track of like merger trees, right? So where do they merge, or if they stay isolated? Yeah, we didn't look into that, but yeah, the Hello mass function. Yeah. It's a power law. So the Hello mass function is a power law fitted by a minus 0.7. It's pretty much consistent after equality. So what will change here if you move with time is the large mass cutoff, because you're allowed to form larger mini cluster halos because they merge. Yeah, that's what we see. So we see that the energy saturates because essentially they don't have any more space to grow because they reach the boundary of the mini clusters. That's the typical size of the QCD, or the horizon at QCD scale, at the QCD time. So essentially what you see in co-moving coordinates, that these areas cannot grow larger because they are bounded by the mini cluster themselves. And that freezes the ratio of void density to the average density in co-moving coordinates, which is this plateau that we see here. So in principle, if you were not if you had like a homogeneous background, you would expect that this void would keep the void energy would keep decreasing, but because the void can also expand indefinitely. But these voids they cannot expand in volume. Sorry, say again. So what we see is that all the accents that are under dense region that get dragged out of these empty regions, but then these empty regions will not grow in size. Is that related to your question somehow? Yeah, but maybe we can discuss more. Yeah. Sorry. So what was the question? Tidal disruption? No, of course not, because we are Z of 100.
That is what by the
yeah,
that is what by
By-
stars in the galaxy.
okay, so you can do bodies here, like, do you? Okay, so no, but I guess that's why it's contemporary.
Yeah, that's the point. That's the point. That's the point. Yeah. We're missing a lot of dynamics, but the argument is that we can put a lower bound. Yeah.
By directly this race mode stuff, how do you think the pressure in the body is so much here.
Yeah, so,
Bodies are really equivalent to this.
yeah.
They become what's the mass?
The mass of. So they can be as low as 10 to the minus 12, 13 solar masses. And they, as they merge, they can get up to 10 to the minus 6 solar masses or something. They cannot get larger than that because then
You have like